Welcome to the Explainer. Let's just jump right in, because today we are embarking on a seriously fascinating journey. We're going to take a guided tour of quantum computing, and we'll be moving from the mind-bending, honestly almost magical, abstract theories of the quantum world all the way to the massive, freezing, real-world machines that are running these calculations today.
But look, before we get into the heavy science, I've got to ask you a simple question. If you want to drive a car, do you need to understand exactly how the internal combustion engine works? Of course you don't. You just need to know how to use the steering wheel and the pedals. Well, it is the exact same thing here. We can completely understand the incredible functionality of quantum computers without needing a PhD in advanced physics. So take a breath, relax, and let's explore this together.
Here is our roadmap for today's explainer. 1. The quantum world. 2. Superposition. 3. Measurement. 4. Quantum gates. 5. Entanglement. And 6. Inside a quantum computer.
Section 1. The quantum world, a matter of scale.
To really wrap our heads around this revolutionary tech, we first have to understand the scale we're dealing with. Basically, we have two different rulebooks for our universe. On one side, we have classical physics, the stuff we all learned in high school from Sir Isaac Newton. And this classical theory works phenomenally well for predicting cause and effect for objects the size of a building, a coffee mug, or a football. But when you zoom way in, down to the scale of nanometers, classical physics actually becomes inaccurate, and that is where quantum physics steps in. It's effectively a refinement of classical physics that is absolutely necessary to describe what happens to the tiniest particles in our universe, like electrons and atoms. Section 2. Superposition and qubits. Multiple states at once.
And that brings us to the first of our 4 highly surprising quantum phenomena. This is the foundational building block for something called a qubit, which is just short for a quantum bit. Now, in the classical world, a computer bit is strictly either a 0 or a 1. A particle is in exactly one place. But in quantum mechanics, many different measurement outcomes can be somewhat true at the exact same time. So picture a quantum particle splitting into multiple opaque copies of itself, just spread out over space. The darker the sphere is, the more presence or likelihood it has of being found at that specific location. It's literally in multiple positions at once. And a qubit does the exact same thing with data. It can store a 0 and a 1 simultaneously.
So why does any of that actually matter? Let's use a practical example. Imagine you have 46 different Excel spreadsheets, and each one takes exactly 1 megabit of memory to store. On a regular classical hard drive, you'd need 46 megabits of total memory, allocating space for each spreadsheet one by one. But a quantum memory in superposition works totally differently. It theoretically has the option to encode all 46 of those spreadsheets using the equivalent of just 1 megabit of qubits. It stores them all simultaneously.
Section 3. Quantum measurement, the catch of decoherence. Storing data that compactly sounds like an absolute cheat code for reality, right? Well, there's a catch. This is where the weirdness of quantum mechanics brutally meets reality. The crucial point here is that we can't just peek at all 46 of those spreadsheets whenever we feel like it. In quantum mechanics, any observation, even the slightest peek at our system, is essentially a destructive measurement. The very moment you measure a qubit, it instantly jumps out of its superposition and collapses entirely at random into a normal classical state, like a solid 0 or a 1. All that rich, simultaneous data, instantly deleted. For engineers building quantum computers, this is terrifying. It's a process called decoherence. Basically, no matter what materials we use, qubits naturally interact with nearby particles in the environment, and those random interactions act just like destructive measurements, completely ruining the superposition. Section 4. Quantum gates, programming qubits. So if measuring the data destroys it, how on earth do we actually run calculations? Well, to process quantum data without destroying the superposition, a device uses what we call quantum gates. Unlike the destructive and random measurements we were just talking about, quantum gates are rapid bursts of physical forces that change the state of the qubits. A gate takes an input, say a little magnet pointing up, applies an operation, and outputs a changed state, like the magnet pointing down. These operations are highly deterministic, which means their input-output behavior is reliable and consistent. They manipulate the data while managing to keep that super delicate quantum state fully intact. And when you string those gates together, you get something pretty amazing. If you take a list of written instructions using a language called OpenQASM, you can translate that exact same code into a graphical format called a quantum circuit. Horizontal lines represent individual qubits, and time just flows from left to right. Whenever there's a colored box on a line, that means a specific quantum gate operation is being applied to that qubit at that precise moment in time. It's brilliantly designed. Honestly, reading a quantum circuit is very much like reading sheet music.
Section 5. Entanglement, a quantum mystery. Now, this final abstract phenomenon has a notoriously difficult and mysterious flair to it, but it's incredibly powerful. Let's just walk through a quick thought experiment step by step. Imagine we have two qubits here on Earth, and we perfectly entangle them so they exist in a shared superposition. Basically, they'll always yield identical measurements. Now, computer scientist Alice takes one of those qubits on a rocket ship and flies it all the way to the dwarf planet Pluto, while physicist Bob keeps his qubit back here on Earth. Once she's on Pluto, Alice measures her qubit and finds the outcome is a 1. Because they are entangled, we now know with 100% certainty that Bob's qubit on Earth will also instantly collapse into a 1. But how did Bob's qubit know that Alice made a measurement millions of miles away? The theory of relativity tells us that information cannot travel faster than the speed of light, and yet these two qubits act in perfect unison instantaneously. It completely defies classical logic. And while we can't use this for faster-than-light messaging, these correlated outcomes between faraway qubits give us entirely new functionalities for quantum networks. Section 6. Inside a quantum computer, looking at real hardware.
Okay, take a breath. We made it through the 4 phenomena. Now, let's shift our focus from abstract awe to concrete reality. Let's step inside the labs using some incredible photos graciously provided by the Quatech Research Institute in the Netherlands. The real quantum magic actually happens on a tiny electronic circuit small enough to be held by a pair of tweezers. It's really not totally unlike the computer chips inside your smartphone. On this chip, tiny electronic circuits restrict the flow of electrical current to act as bit states 0 and 1. And because it's quantum, that electrical current can exist in a superposition. You literally have electrons participating in both a 0 flow and a 1 flow at the exact same time. But as we learned earlier, quantum states are incredibly fragile. To prevent the environment from destroying this data, this tiny chip requires absolutely extreme conditions.
How extreme are we talking? Try 10 millikelvin. That is literally 1/100th of a degree above absolute 0. That is the mind-numbing temperature required to make these electronic circuits superconducting, which allows the electrical current to flow indefinitely without any damping or unwanted disturbance that would ruin the qubit's state. And to achieve that freezing temperature, engineers have to place that tiny chip at the very bottom of a massive structure. It looks like an iconic metal chandelier, but it's actually a dilution refrigerator. It's suspended right from the ceiling, and it cools the hardware down in stages. The top disks might sit at a freezing 35 Kelvin, but as you go down layer by layer, it gets increasingly colder. 3 Kelvin, 900 millikelvin, 100 millikelvin, all the way until the final stage at the very bottom hits that magical 10 millikelvin mark, where the chip actually lives. Now contrast that elegant, freezing, isolated tiny chip with the chaotic mess of classical wiring that's absolutely necessary to control the qubits. To execute a quantum gate or read a measurement, we have to send microwave frequency signals from room temperature electronics all the way down into the freezing fridge. Right now, it takes about 2 to 4 separate wires to control just a single qubit. So while we obviously want to eventually scale these computers up to millions of qubits, you can quickly see the massive engineering challenge here. You simply cannot connect millions of physical wires to a tiny chip without letting heat and noise leak into the system.
So let's bring it all together. What should you really take away from this explainer? Just remember these 4 core building blocks. First, superposition. Qubits can store data like 0 and 1 simultaneously. Second, measurement. The big catch is that observing this data probabilistically destroys that superposition. Third, gates. To actually compute anything, we use deterministic operations called gates to safely manipulate the qubit states. And fourth, entanglement. Qubits can share correlated outcomes over vast distances, totally defying classical physics. Which leaves us with one final kind of wild thought. Today's quantum hardware occupies entire rooms. It requires massive dilution refrigerators, uses chaotic webs of wiring, and consumes about 25 kilowatts of power, which is roughly the same as driving an electric car. It honestly feels exactly like looking at the giant room-sized classical computers of the 1940s and 1950s. But look at how classical computers evolved. They became compact, efficient, and powerful enough to fit right in our pockets. If we are truly living in the 1950s era of quantum computing right now, just imagine where this revolutionary tech is going to be a few decades from now. Will you have a quantum computer sitting on your desk? It is a pretty thrilling question to ponder. Thank you so much for joining me on this explainer, and as always, keep questioning the world around you.